So welcome. Thank you all for joining us this evening. We have a great program, I think. Wonderful speaker to educate us on kind of some new dimensions in water quality.
Well, some of you know me. Some of you are new faces. So my name's Daniel Amato. I am, I guess, a water quality scientist. Graduated from Manoa 2015, and I've done a lot of work here on Maui as part of my work. I'm currently working in an American Samoa using similar techniques, but also bridging out into the microbial world, into the coral DNA and protein expression world. Some of that data, unfortunately, is not available yet, so I can't really give you a sneak peek, but I will talk about what we're doing down there and how we're kind of moving on with the science and making up new protocols and things like this. Well, my talk today will mostly focus on is how we've used algae as a bioassay and a water quality tool here in Hawaii. I'm going to give you a fair amount of information about Maui. For some of you, you probably have heard this before or read it in the newspaper or been directly involved in these studies. But I think it's to me it's super interesting. So I'll go a little through the history of the work that's been done here and how it's influenced my work and what we knew, what we now know, and where we're still going with all this. So really excited to be here, and I guess without further ado, we'll get it going. All right, so briefly go over some common pollutant transport pathways, talk about seaweed as a water quality indicator, previous studies on Maui. I'll go into kind of two main studies. There are a couple different studies kind of all put together, but I kind of separate into study A and B here, where we're talking about the groundwater as it transports nitrogen to Maui reefs, and then the fate of wastewater on Oahu, again, that nitrogen transported through groundwater. Touch a little bit on current work in American Samoa, and then wrap it up with some conclusions. So pollutant transport pathways is, some of these scenes are probably pretty familiar with you. Actually, in my day job, my current job, when I'm not out in the field doing the hard science, I do a lot of stormwater quality work as a consultant for DOT right now. And so some of these scenes I deal with every day, water flowing into inlets, is it dirty, is it clean, what's influencing it? All that really determines what our coastal water quality is like. And so scenes like this, up here with these sediment plumes, if you've ever flown over these main Hawaiian islands after a storm in the morning, you may see this like red ring around Molokai, and as a water quality scientist, I look down and just go, ooh, I do not want to be in the water there today, and no one probably should be. So talking to some of you before my talk, it's clear that you're involved in water quality science. I also volunteer at Certifier Foundation. We have our own blue water quality, blue water task force, and so it's really important, I think, that we pick up where the state kind of leaves off and test the reefs, test the water, put that information out there on the web. So I'm definitely a full supporter of that. And hopefully some of my work will influence you to maybe use a few more tools when you have questions that you want answered. So when I kind of first came to it seemed clear that streams were well documented. We had flow gauges on a lot of the major streams. We knew what the nitrogen loading rates were most of the time, or at least we thought we knew. And what was left kind of really untalked about, but yet ubiquitous in these environments, is this submarine groundwater discharge. And so this can be defined as a direct discharge of groundwater across the sediment-water interface. And this happens wherever there's a coastal aquifer that's connected with the sea. And so, you may have felt this when you're swimming, typically around low tide, where you'll get like a cold spot, and you'll kind of tuck your arms in while you're snorkeling, and you're like, ooh, probably groundwater. And so this has the ability to basically transport anything that's dissolved in it, such as fertilizers, pesticides, herbicides. and even wastewater to coastal waters. Here's a video I took right here in Kihei at Kalama Park. This is right kind of in the heart of wastewater plume, if you will. I'll go into that a little later, but just keep this in mind. That's just an example of groundwater discharge at the beach face at low tide. So just to kind of give you a little bit more of a diagram of how this works, it rains in the mountains. That rain percolates down through the ground, through the rock, and it hits the water table. And along that flow path, it can pick up fertilizer nitrogen, typically, which was very prevalent just recently here as sugarcane fields. It can pick up natural nitrogen in that soil. It can pick up, and as it flows to the ocean, which is kind of the end destination for groundwater, for most groundwater on these islands, it flows towards the ocean. It can pick up wastewater that's coming from injection wells, from septic tanks, cesspools, and carry that in the ocean. And so this becomes an issue because we have very high sources of nitrogen, so high nitrogen content in that water, and our ocean, most times in natural conditions, is very low nitrogen. We call it oligotrophic water. And so any addition to that, any nitrogen addition to that ocean water can potentially offset that really fine balance of nutrient cycling. Where it's like, I kind of look at this like the wastewater, the fertilizer, you're fertilizing the reef, you're like fertilizing your lawn. Okay, so the lawn, you fertilize the lawn, lawn's gonna grow. Just, you could think of the grass like seaweed. And if you don't have fish are the lawnmowers, the seaweed keeps growing. So this is this delicate balance of having enough fish to keep the lawn mowed and not adding too much fertilizer to make it grow really fast. And we'll talk a little bit more about that kind of herbivore nutrient balance in just a moment. So pretty nice scene here. We have healthy reefs here on these islands. This one was taken on Maui, I believe, Oluwalu or Kaikili. And in some places in the past and currently we have what we consider degraded reefs. And this is kind of a classic picture from Kaneohe Bay not too long ago. And so just to kind of browse through a couple of the disaster marine weeds that we've come across and I've worked pretty closely with over the years. We have Gracilaria salicornia, commonly known as the gorilla ogo. Does this exist here? Does anyone find it on the reef? A little bit, really? Where?
Waihe'i, there's still a little bit we find once in a while. But
okay. So you're
pretty much gone.
Gone in the sense that it's been removed, or that it's just not really ever been a problem?
Well, as I've been told, that when they had all the pollution coming out of Papui Harbor back in the 70s, 80s, they ended up losing so much of the algae along that shore, what hit the shore and over, and it just hasn't come back.
Okay.
I don't think we've had that Gracilaria.
Yeah. But I did a fair amount of work in the Wailuku areas, and yeah, I didn't really see it either. This one is pretty prevalent, and this is kind of another classic shot of the beach rack. I love that word, rack. This is kind of the sunset area. You can see Molokini in the background. This was, I guess, what year was this happening? 2002, when this was really an issue. Sunset Beach, algae cleanups causing a ruckus in Kihei. And Acanthophora spicifera. This is probably the most prevalent invasive algae on the islands. I found it almost everywhere. In some places, it does this and grows in these big mounds, causes problems. In other places, it's just kind of a piece here and there. Eucuma denticulatum, mostly confined to Kaneohe Bay. It's largely been controlled for the most part, but I think still definitely an issue. But I want to just, keep in mind that as I show all these horrible algae pictures, it doesn't mean that algae is bad. It's actually it can be good for an ecosystem. There are many ecosystems that are dominated by algae naturally. In northwestern Hawaiian Islands, there's reefs that look like this, and they're just it's a native algal reef. It's very diverse. There's not one species that overtakes everything, and so All algae are not bad. But when you have invasive algae, and that doesn't mean that they're from somewhere else or alien invasive algae. They could be native algae that become invasive, and they can become invasive when you create the right conditions, slamming them with nutrients, taking out the herbivores, and so again, nutrients definitely a threat worldwide. This is some of the most ridiculous algae blooms that I've seen in my lifetime through pictures were from the Yellow Sea in China. And so I got a couple photos of that, but it was just, the scale of this bloom was pretty amazing. So algal blooms in general cause a lot of issues. They compete with native species, they block light, they do take nutrients that would probably be available to them. They physically abrade corals. Just the presence of them can cause certain coral diseases, and the list kind of goes on. Economic impacts, and this is what usually gets regulators to kind of start paying attention, is when you start adding dollar signs to these blooms. So the China bloom was estimated to cost about $100 million in cleanup efforts and lost revenue. The US EPA estimates about $1 billion lost to US tourism per year. And then going back to our classic Hypnea bloom Kihei shot here, there was a 2004 study that estimated 21 million loss to this area here per year by this algal bloom. And so just one last photo of the scale of this algal bloom. This is what we're trying to avoid, obviously. So getting back to kind of that delicate balance between nutrients and herbivores, this is one of my favorite ways it's ever been presented, and it was kind of a concept that was really elucidated by Littler as a kind of a husband-wife team and their colleagues that published on this over the years. And so this comes from their 2006, and so basically this, looking here, we have on the right grazing activity, and on the top grazing activity, and on this axis over here we have nutrients. And so high grazing activity in the top left here and low nutrients gives you kind of this, what we'd probably consider a healthy reef, massive forms of corals, encrustose, coral and algae. And then as you move towards either axis or in this direction, things change. So you reduce grazing activity, you get turf algae, or you get turf algae buildup. You elevate nutrients, but you keep grazing high, you get crustose, coral and algae. But the kind of double whammy, you reduce grazing, say overfishing, you increase nutrients, say fertilizer or wastewater, and you end up with frondose macroalgae, and that's essentially what would be considered an algae bloom or excess algal growth. And so Jen Smith, who you may have read some of her papers in the past, did pretty much an experiment on this theory. So it involves caging tiles, fertilizing some, caging and fertilizing others. And so you get that kind of, this is the caged, fertilized slide. This is, mind you, only after a few months, so we're not going to see massive coral growth in the top left. But we see the difference here. We have kind of an overgrowth of frondose macroalgae with no herbivores and nutrients, and that's kind of the point here. And mind you, studies by Megan Daler, who could not be here tonight, and my mentor and advisor Celia Smith showed that you can actually reverse this situation. So they did something similar to this, and then when you pull the cage off, you reintroduce the herbivores and you cut off the fertilizer, you get fairly quickly back to something that resembles the original state. And so that's really promising. That shows that reefs can be resilient if you create the right circumstances, if you bring the herbivores back, or, in practical terms, you stop fishing certain areas for certain species, etc., and you cut off the nutrient source if possible. So my work has largely focused, this has been a large part of my work, which is using seaweed as a bioassay. And so for a bunch of reasons, mainly that a chemical, a grab sample or conventional water sampling is basically a chemical snapshot of water from a single moment in time, whereas seaweed integrate nutrients and the water conditions over time. Nutrients will be taken up as soon as they're available by an alga. So, for instance, if you have sort of a pulsed environment, like in a groundwater scenario where at low tide you get these pulses of groundwater, that alga will absorb those and hold on to them. But if you happen to take a water sample at high tide, you might miss it entirely, and it would look fairly, ambient, if you will. Mixing quickly dilutes these nutrients, so that seaweed are basically considered an ideal indicator of water quality because they do integrate all sources of nitrogen over short time scales and sometimes long time scales, depending on what alga you're looking at. They're typically attached to a surface, which means that they're fairly easy to find and collect. They're easy to grow in the lab, and the fairly low analytical costs as well. So this is some of the work from Daler. She did this, I believe, out of a lab here on Maui, where she grew different types of algae in different wastewater effluent levels. Okay, and you can see that with this increasing wastewater, you have an increase in tissue N that's really linear. It's a pretty tight relationship, showing that the alga is a really good reflection of the water that it's bathed in. Now here's another metric that I'll introduce. This is delta 15N. This is kind of the isotope signature of that alga, and that will also reflect the wastewater. And I'll explain this just a little more in a moment. But I just want to point out that these species also track the wastewater effluent really well with this metric as well. So just to get a little bit more into stable isotopes, basically delta 15N is a ratio of the light isotope of nitrogen to the heavy isotope, so that's N14 to N15, and that's compared to air as the standard. So this algal tissue delta 15N reflects coastal water delta 15N, and it looks something like this. This is an image from Hunt and Rosa showing you sort of the delta 15N scale here. So 0 here would be basically air as the standard, and using algae, or you could test water itself, but measuring the delta 15N of that sample, you can get a better idea of where the source of that water or the nitrogen in that alga tissue came from. And so if, for instance, we got an alga off the shore, sent to the lab, and we got a value of, let's say, 4. Well, looking at this scale here, it's kind of ambiguous. We have natural soil N in that range. We've got some kind of the fertilizer sort of in that range, and wastewater in that range as well. So it's kind of ambiguous. Not a lot of information we can get out of that. However, if you have a much higher value, you're in like this wastewater area. And I say wastewater, but basically it means that nitrogen came from a process that involved denitrification, and that would drive this value up higher. And it typically happens in wastewater facilities. It happens in nature at times. It happens in cesspools, septic tanks.
That's not the signature of agricultural runoff.
No. So that would be agricultural where they're using fertilizer. So fertilizer, industrial fertilizer, largely comes from air. That nitrogen is sequestered from the air. So it has a value that resembles air. So if you look at these fertilizer ranges, they're generally in the 0 range. They can be kind of +3 to -3, +4 to -4, but they generally center around 0, somewhere in that. And so in my 2016 paper, I attempted to combine these two metrics to kind of get a better idea. So that's the tissue, the tissue N in percent, and the delta 15N signature, to try to figure out how we can tease apart this fertilizer values and wastewater values a little better.
Daniel,
Yes.
how do you get negative values?
How do you get negative values? Again, fertilizer itself is in that range of -4 to 4.
But this is
It's
the
the-
percent of nitrogen 15.
It's the ratio of nitrogen 14 to nitrogen 15 of the sample reference to the standard. So that the standard is 0, but your sample has a ratio that's lower than that, then you'd have a negative number.
And 0 is the ratio of air.
Right. So compared to air, it could be a ratio below air or above air. Does that make sense?
Thank you.
So if we look at this range, and this is kind of, I don't want to put a definite number on it. So it's kind of a range 7 to 10. Beyond to the right of that, I'm going to call generally high, a high value, and to the left of that, I'll call generally low. So if we had an alga that had a high delta 15N and it had a relatively high amount of nitrogen in those tissues, it's a case that it's an indication that the nitrogen in that alga came largely from a wastewater source. Conversely, if we have a high amount of nitrogen in the tissue, but a fairly low or relatively low delta 15N, that would indicate to me that it could be fertilizer driven. You have a fertilizer providing the nitrogen, it has that lower signal, and so we point to fertilizer. And again, this is all relative to what's in the environment. If you're collecting algae next to a wastewater plant and you get a high value, it's just more evidence that it could be wastewater. If you're collecting it next to a large sugarcane field and it looks like it has this sort of a signature, more evidence that you have a lot of nitrogen that's provided to these plants in the ocean. And a third case where if you have low values of both metrics, it's a little ambiguous, but it looks very similar to what you'd find in the more pristine areas. So I'd be tempted to call that potentially natural. All right, so this is a paper you may be familiar with. Megan Daler, Robin Knox, and Jennifer Smith, and Celia Smith, some heavy hitters up there in this kind of work. This is the paper that kind of really got me interested in Maui, got me interested in working here. And so basically Megan went around the island in a very large effort, collected lots of seaweeds, combined them all together at the site, and got their delta 15N value. And I know that the values are kind of blurry on here, and I apologize. I just couldn't get a better screenshot off the PDF. But we look at our Lahaina wastewater facility here, and the value that's highest offshore here at Kalikili Beach Park is 43. And so at Kahului Harbor, another high value for this map, 22. And Kihei wastewater reclamation facility, we have a 17, so a little bit lower. But basically what we find is we get our highest values right next to these wastewater facilities that utilize injection wells as their primary disposal method. And so this is a little clearer going in, a little closer here. Kihei at 17. So we're going to kind of talk a little bit more about Kihei. This is some work from Hunt. This is Charles Hunt, who's worked at the USGS for a while, and he made an effort to map the plume from the Kihei facility. And so where you see in red, that's like the most concentrated, 80 to 100% effluent, and then the values or the colors kind of indicate that that percentage of wastewater getting less, all the way to dark blue, which is 5 to 20. And so working alongside Megan Daler, collecting Ulva at this point, collected algae offshore here, where you can see these squares, and the values indicate the delta 15N number. And you can very clearly see that these highest values shown in red are directly within that kind of estimated plume area where you'd have the most concentrated wastewater. And again, going back to the video I showed earlier, that was taken right here at Kalama Park, of water spilling out at the beach at low tide. And so again, it's just really good relationship between modeled water flow and algal values. Again, note that here the water going in is at the value for delta 15N is at 15. coming out at the beach. In the algae, we have 15s, 16s, 18s, etc. So pretty good agreement there.
There's not a big plume though, Mackay, of the Maui Meadows, which is mostly cesspool and septic.
There's Maui Meadows. Is that
It's
more
further south of the wastewater plant.
further south?
It's on the map on the
Yeah.
prior slide.
I haven't. I don't know a whole lot about that area, honestly. I can't comment on that. Okay, so this is all well and good, and I fully think that algae are a great indicator. But when you're trying to present data to a jury in court, you need something with a little more certainty, if you will. So. One of my advisors at the time, Craig Glenn, and my colleagues decided that they were going to do a dye test. And this is probably the most definitive way to tell if you have wastewater that's from a wastewater plant on your coral reef, is to put dye into the plant and then measure it as it comes out on the reef. So this is kind of what it looked like. They did a 24-hour dye injection into the injection wells. They were mixing dye and then dumping it in bucket by bucket for 24 hours. And basically the conclusions were basically irrefutable evidence that there's a hydrological connection between the wastewater facility and the ocean. And I think this was kind of a crucial take home, because in the past there wasn't a whole lot of evidence that they were connected. And although these facilities were engineered to put wastewater in the ground and have it come out in the ocean, it was kind of unclear where it would come out. They knew it would come out in the ocean, but they didn't know it was going to come out, in 2 feet of water, or really deep, or which direction it was going to go. And with this plant, it's really interesting because the subterranean hydrology here was such that the water path, instead of going straight out and discharging here, which you might expect just because it's the shortest path to the ocean, it followed maybe an old riverbed, and the water flowed south before coming out here at Kahekili Beach Park. And there, with the dye, and you can measure the concentration you put in, you can measure it coming out, and you can calculate all kinds of things like the travel time, the concentration, etc. And so there was a 3-month minimum travel time. So 3 months after the dye went in, they saw the first signs of it coming out. But in general, it was about a 1-year travel time on average. And on about 64% of the effluent, from these calculations, they were able to estimate that 64% of the effluent from the well that they put the dye in is coming out right at the Kahekili Beach Park in this kind of North Seep Group and South Seep Group. Other ways that this group detects groundwater discharge, you can see here, this is what's called a TIR map, so all the colors offshore here, that's, you fly a plane, or now we're actually using drones, and we're flying with thermal cameras over the reef, and we can see where the groundwater is. Typically, this map would look dark blue, where this groundwater would show really cold, because groundwater typically is colder than the ocean. But in this particular case, the water coming out of these seeps was warmer than the ocean. And that could be because, for a number of reasons, because it's warm going into the ground, it's warmer than the groundwater going into the ground. But there also is a lot of evidence for a lot of microbial activity while in that flow path. And that's a really interesting thing we can maybe talk about later if we have time. I got some hypotheses that have not been really answered yet. But I don't know if I have a whole lot of time to get into that, so we can talk about that later. Again, some of the values, so this area also, simultaneously with the dye injection, there was also a fair amount of algae work being done. There was water sampling for Delta 15N, and you can see right in this area here where we have this hot water plume from the wastewater plant. We have the North and South Seep groups getting a lot of that injected dye coming out. We also have really high values for Delta 15N in the algae and in the water itself there. Now, mind you, I would like to say that the amount of nitrogen in those water samples was actually fairly low, lower than going into the injection well. And again, I think that plays tribute to some of this bacterial activity that's taking place, denitrification along that flow path. It's almost as if there's a natural cleaning process for it on, as it went out, and it was coming out fairly low. But then I don't know if I want to get into it, but they decided to start chlorinating the water. Bacteria started to die, and that nitrogen level went up a little bit. So that's kind of another story for later if we have time again. So all that work that was done during or before I was involved in this project kind of, led me to, okay, well, we know that Lahaina, there's a connection between the facility in Lahaina and the ocean, and there's evidence that the same thing's happening in Kihei, but no one's interested in or talking about the Kahului wastewater facility that has the highest volume. They do about 4.5 million gallons a day, and so that kind of spurred my interest, like, well, maybe I can go and do similar work, but more, maybe more thorough, use more techniques, and just kind of find out what's going on in Kahului. And so to do that, we kind of studied multiple areas. We studied more natural areas. We studied wastewater areas. We studied areas that we thought were affected by fertilizers, and we compared them all. The hypothesis was that locations with high nitrogen in coastal groundwater will have high nitrogen in algal tissues, and also that coastal marine water compared to locations with low nitrogen in coastal groundwater. And so again, making this connection between the groundwater really impacting reef water, and that's kind of the point I'm trying to drive home today, is that streams obviously are, and streams and rivers obviously have a large impact on the reef, but this is something that we commonly don't see all the time, and we should definitely consider it when we're looking at the reef and wondering what's really playing into this reef health and what's going on. So the studies that we worked in on Maui, we chose what we thought were some high nitrogen loading areas. Kuau Bay was kind of our sugarcane land fertilizer impacted area. Kahului Bay near the wastewater facility there, potentially our wastewater impacted area. And Ma'alaya Bay, as some of you may know, has kind of had these questions looming in the past. Do these small pocket injection wells of the condos, are they influencing the reef? Or is it the sugarcane fields? What's really contributing to reef decline in Ma'alaya? And so we wanted to take a look at some of those questions and try to use these techniques to parse that out. Some more of the natural areas we worked in were Maui Nui Bay on the northeast shore, Honolua Bay, which definitely is not as pristine or natural as Maui Nui Bay, but fairly healthy, and Waiahu Bay, which we initially thought maybe may have some impacts from cesspools and septic tanks, because there's a fairly high density of those upslope. But as it turned out, we didn't really find a whole lot there. So our methods were to collect algae onshore, similar to a Megan-Daler approach, where we collect algae that exist at the shoreline. We collected all the species, the Acanthoptera and the Hypnea. But in addition, we also deployed algae. And so we deployed ulva in cages like this. They're basically plastic cages with nylon netting. We kind of put them just below the surface, about 1/4 meter below. And that was because, in general, the groundwater tends to, it's a little more buoyant than salt water given its density differences and its temperature. So it tends to kind of float on the top surface. So if we wanted to catch that groundwater, we were going to look for it in that kind of first, the top of the water column. And so we took these algae tissues and we tested them for delta 15N and nitrogen percent. That's the tissue nitrogen. We also sampled water from the ocean surface. We sampled coastal groundwater, which I'm defining as beach pore water or springs that we would find at low tide. So beach pore water is basically just, we stick a tube into the sand and we hit a pocket of water. It's usually only a few feet down, and we pump that out and sample that. We also looked at benthic cover and diversity in all these locations using underwater photography. And in addition, alongside this study, we also were measuring groundwater using radon gas measurements. So this is a RAD7 or radon in-air detector, and we would motor around, pump water off that top water layer of the ocean, run it through the RAD7, and compare the radon gas in that surface water with a reference, some like wells and the springs that we were finding at the shoreline. And by doing a bunch of math, we can figure out how much groundwater is flowing out, what the flux per day per square meter of shoreline is, and then also calculate nutrient loading to those areas. And let me just say that, so we did that motoring around, but we also did it over a series of tidal cycles. And so that's kind of the mobile setup, and this is the stationary setup. This is set up in Honolulu Bay, and we would just kind of, this is kind of the water intake here and our water quality multimeter. And that would just, over a tidal cycle, pump water into this device and measure that water discharge throughout time. And I'm not going to go a whole lot into the groundwater. This is kind of for nerdy hydrologists. Some of you might be in the audience, and I'm really and so I really like this work, and I've done a lot with this geohydrology. But I'm just going to kind of summarize what we found briefly. In general, SGD is really patchy, and you can kind of see that by the various colors throughout our tracks here across our sites. In general, we have our max flux near low tide, and that's in, it doesn't always happen, but in general, if you want to find groundwater, you should go at low tide. That's why I usually tell people to swim at high tide in areas where they are, maybe concerned about what's upstream or upslope. There's also a max flux near shore. And so you get higher nutrients in this groundwater discharge at low tide near the shore. You get a lowered salinity typically if that discharge has a lot of fresh water in it. And it typically has a lower temperature, again, filling those cold spots on the reef as you swim around. And so using these radon techniques, we are able to estimate groundwater discharge and the scales here up to about 6 cubic meters per meter of shoreline per day. And this was just officially published in Bishop et al. 2017. It was kind of released for a while, but never officially published. But now it's got actually a year associated with it, so that's good. And so, yeah, if you're looking more for nutrient loading and that angle of this, the groundwater discharge angle of this work, I would direct you to that paper. But I'm going to focus on mostly the comparing algae to the coastal water quality today. So this is a graph where we compare these 3 suspected high nitrogen loading locations with our suspected low nitrogen loading locations. And marine DIN, that's dissolved inorganic nitrogen, is shown on this kind of hashed blue lines, and we can see it was highest at Kuau, Ma'alai, and Kahului, and then a little bit at Honolulu, but Honumanu and Wai'ehu were fairly minimal. And so these green circles here are the average ulva nitrogen at that location. So that's the average of all the ulva that we deployed in these locations that was in the cages, on close to shore and offshore. And we can see that in our suspected low nitrogen loading locations, we have, around a third less nitrogen in those tissues. So around 1% nitrogen in those tissues, as opposed to Kuau, where we had up to 3% average. So That's a large difference. So let's go now to the north shore of Maui, Kahului Bay, Kuau Bay. These are some sites that we worked. And along the north shore, I took some of these photos. Actually, no. I took most of these photos. I didn't take that one. That was underwater. But we have Ulva washing up here at Kite Beach alongside turtle turds. Got to watch where you step, I've learned. This is a huge hypnea bloom that washes up at Tavares Bay, at least during the time that we were there, and kind of sloshes around in the water. That was pretty significant. And some more hypnea just kind of attached to the rocks in that area. Again, you have Ulva and hypnea kind of dominating these intertidal areas. And then also another story I'm really not going to get into tonight, but I think is really interesting, is the link between algae like this that are growing in a high nutrient environment and turtle tumors. And so if you're not familiar with that story, I encourage you to look into it. But the short story is that algae that has high nitrogen produces a lot of an amino acid called arginine. And arginine promotes tumor development in many species, including turtles. So that's the link there. Yeah, if you want to talk about that a little later.
Is it promoted in humans also?
I believe it is. I believe it does promote. I know other mammals for sure. Okay, looking a little bit more at the Kuau Bay, I don't want to spend too much time talking about numbers and bore you all to death. But the general take-home is that so let's just kind of orient you a little bit here. Circles are diploid ulva, triangles are shore-collected algae, that's algae from the rocks, the pictures I was just showing you. And then marine surface water is these estuaries, and then coastal groundwater, these are our springs as the stars. And these are all pretty much on the same scale here for delta 15N. And what we can see is that all the colors generally are generally similar. So we have low values of delta 15N in the algae, we have low values of delta 15N in the marine surface water and the coastal water. And these bold-faced numbers here next to the algae values, those are the percent nitrogen in those tissues. So we have up to 4% nitrogen, 4.4 in some of these tissues here. And as you kind of go offshore, that nitrogen decreases. Percent nitrogen decreases. Again, I want to point out the proximity to the sugarcane fields at the time. Less than 100 meters in places, and I'm pretty sure what you know what it looks like going upslope. Fairly significant, very significant amount of sugarcane being grown. If you look at some of the coastal water nitrogen values, I think this is the most interesting part of this table here. This is out of Bishop et al. Kuau Bay, N plus N, or nitrogen plus nitrate, 377. Vastly different from what we found in the more pristine area, Honumanu at 6.4, even Waiegu at 22. Wells generally fall in the 28 area. Basically, our ulva in Kuau Bay had high tissue nitrogen percentage, had low values for delta 15N. Benthic studies showed no coral present, macroalgae at about 70% cover, and that kind of led to low benthic diversity.
So now that we don't have agriculture on Maui, hardly, should we see a reduction in fertilizer and then therefore a reduction in these values?
You know, that's
Is
going
that
to...
kind of a natural experiment we could conduct?
Did I bait that? That was great. That's something that I've had in my mind for probably since I found out that sugarcane was done. And I was like, man, we need to go now and start sampling, because I had the samples from before the fact, and I'd love for somebody to continue this, and because I think that it's really going to show, and this is a natural experiment. We have this massive sugarcane area that was doing heavy fertilization on a pretty consistent schedule, and now it's not happening. So the big question is, how long does it take the aquifer to flush itself? How long will it take these coastal groundwater springs to reduce that nitrogen? I mean, this is the coastal groundwater we're looking at, but if we look at the average value of water samples, and that's all the samples from Kuau at 23 micromolar. compared to Honeymoon 0.18. That's orders of magnitude difference. A very, very significant amount of nitrogen. I mean, we saw some of these seeps as high as 560 micromolar nitrate, which is bordering undrinkable when it comes to EPA thresholds. So yeah, I was definitely going to bring that up today, that I think that we're in a unique place to document the natural experiment and see how that aquifer flushes itself, see where it flushes itself, and even more, how the ecosystem recovers. So I'm definitely excited, and I'd love to, take part in that study. And it seems like you guys are doing nutrient sampling here. So
What's the wells value down at the bottom?
So that's like an average of wells on Maui that we sampled. So that's 28 micromolar is just the average of the wells.
Okay.
Yeah.
So it's a
As
comparison
a
of
reference.
just groundwater that people are pumping already?
Right, so those are drinking water wells, yeah.
Oh, so these were all potable drinking water?
I believe they were, yeah.
I have a question.
Yes.
What years did you collect data?
So this was done from 2012, 2013, and 2014, all around the same time in the summer.
Your algae photos are from that time
Yeah.
period.
Yeah, mostly, the ones I'm showing here are 2013 mostly. Yeah. So, again, Kua Bay, the most likely source of nitrogen was fertilizer, just looking at the landscape and comparing the data that we have, we're going to suggest that that's true. And so if we had to put this on my little chart here, we'd end up somewhere over here, high tissue N, again near 4 for percent N, and our delta 15 Ns were fairly low, around between 0 to 4. Moving on to Kahaluu wastewater facility. This is a wastewater reclamation facility, but they do about 4.5 million gallons per day of treated wastewater. And actually, I think that's injected wastewater. And Steve would probably tell you how much reclamation is. What, 10%, 15%?
Only internally. They don't
Okay.
have any reuse program in that area. Most of the water they treat is injected.
Yeah. So this is basically what it looks like just outside the facility near the ocean, and you can see the proximity of the ocean. It's a stone's throw away from the wastewater injection wells. I believe there's about 8 of them on site. So similar map here, and what we see that's different from the Kuau site is we see a lot higher values. So we see values in red up to 9.7 for algae that were deployed offshore. Short collected algae go up to about 15. This is delta 15N values. But the marine surface water and the coastal groundwater samples that we took get even higher, 44.1 up to 38.4. Mind you, the effluent itself is measured at around 21. So effluent's 21, nearshore algae at 15, and so we're definitely, it's pointing towards having that wastewater as a nitrogen source to the seaweed in this area.
Can you talk about the values going out across the region?
Yeah, so this is one of our better sites in the sense of how the experiment was designed. We really wanted to cover as much area as we could to figure out where the plume is going, how far out, and in which direction. So we kind of did alongshore as much as we could, and then offshore in these 3 areas. And so these values again are the percent nitrogen in those tissues. So you can see it kind of decreases as you go offshore, more or less. And so this sampling regime, we wanted to do some interpolation to kind of define that nitrogen plume. And so with some fancy computer magic, you can interpolate those algal values, those delta 15N values. And so using all these black circles and the triangles, those are the algal values, we can create this interpolation and show that. So like this, we're kind of defining the plume in this as about 8 or 9. So in here is kind of the area that this map is showing that there's a fairly significant wastewater signal. in 1977, I believe before this plant was built, there was a study an engineering study that showed where the expected plume was going to be, and so that's kind of shown by this hash mark right here. And so you can see that it's pretty much falls in line with what was expected in 1977. And so if we had to place an alga on this chart here, we put it about there for on average. Fairly high ulva tissue N and fairly high delta 15N. Looking at the coastal water that we sampled offshore, coastal water values, not too bad, 3.4, groundwater around 28, so not quite Kuau at 377, order of magnitude less. But what we see here is some fairly high ammonia values, 14 really stands out among the rest. And that's just due to wastewater process creating a fair amount of ammonia. So again, we have high tissue nitrogen, high delta 15N, high levels of delta 15N coastal water and groundwater samples. And in the Bishop paper, we do a little bit more isotope magic, where we work with isotopes of water, that's the isotopes of hydrogen itself, and compare that to the delta 15N, and we can estimate the percent effluent in those water samples. And so we get from about 26 to 75% effluent in the coastal groundwater samples that we pulled out of the beach pore water, with a small number of samples. That was 4 samples. So the main source of nitrogen to this area, we would say, is very likely wastewater injectate. Now, I usually kind of glance over Maui Bay because it's similar to the Kuau Bay scene, but I think it's really interesting, A, because we're here, but also because there's been this long-going question about, are all these pocket injection wells? Because so each condo has its own wastewater facility, very shallow, 80-foot injection wells that service that one facility. And in the past, this reef here has been covered in ulva. In 2012, when I was here, it was covered in ulva, and then the next year it was gone. So I don't really know what was going on with that. But either way, we did a very similar approach, an identical approach. We did some offshore transects, we did some alongshore transects, and you'll notice that this picture looks very similar to what we found in Kuau. And this is, along the lines of the same results that Steve Dollar found when he did a fairly large study out here. And he said, the injection wells at these condos have probably some influence. It's a minor amount compared to the significance of the nitrogen from fertilizer. And so we're getting basically a fertilizer value. We have low delta 15Ns. We have high, relatively high nitrogen in those tissues, leading us towards kind of a fertilizer value here. Looking at some of the water quality, definitely higher than Kahului for this coastal groundwater. We have 190. It's in the same order of magnitude as Kuau Bay, and our coastal groundwater, our coastal water is at 12, about 4 times higher than Kahului. So that fertilizer influence, I think, is really coming through in those high nitrogen values.
Daniel, would you go back to that last slide?
This one?
On the bottom, shouldn't that be fertilizer?
Yes, you're right. This is an unfinished slide. I threw it in last minute because I really want to talk about Maui Bay. But yeah, the main source would be fertilizer. Sorry about that. So looking at the benthic cover of these areas, and this is again photographs along transects on these reefs, we see these 3 areas, or these 2 areas that had some of the highest nitrogen in those coastal waters. Kuau Bay, Maui Bay had the most macroalgae, and that's shown in red. And as you kind of go to the right here, we have this increase in turf algae shown in green. And then we get to Kahului, and you'll notice this large purple bar here. And that is something that I haven't seen anywhere else in in Hawaii. Offshore Kahului, in about 2-3 meters of water at the most, was this massive underwater bed of zoanthids. And I've seen zoanthids around the Hawaiian Islands. There's usually one here, a couple here, maybe a small patch here or there, but never approaching 100% cover. And so it looks something like this underwater, just a thick fleshy mat of zoanthids. They are potentially toxic to humans if you mess with them too much. They do photosynthesize. They're kind of like corals without a shell. Have you guys been out there and seen this before? I know Donna has. Has anyone ever seen anything else like this on Maui or the Hawaiian Islands? Massive cover of zoanthids. Yeah.
We used to see it all the time back in the early 70s.
Really?
Down at the LOI.
At the Alawai.
Just on those, offshore with the shallow reefs and the people will be out spearfishing at night. Heavy coverage.
Really? Yeah. I imagine Kaneohe Bay may have looked like this in the 70s and 80s as well. I have read some reports of lots of filter feeders and zoanthids. So.
But actually, if you go out in the east end of the island here, Mo'olea, there's we have the limumaki, the poisonous zoanthids there, and there's tide pools that are full of stuff like this.
Wow. Yeah. So that was pretty wild. I'd never seen anything like that. How am I doing on time here?
6:05.
Yeah, go.
Go. Okay.
Good.
All right. So on Oahu, I was really interested in OSDS, or on-site sewage disposal systems, in addition to wastewater injection, because it does happen over there. Maybe not on the scale that we have here on Maui, but I wanted to really take what Whittier and LKD did, and they basically took all the state's data and did a GIS map of all the cesspools and septic tanks that they knew about, and came up with these great density maps that kind of pointed me like, oh, can I find wastewater over here? Look at the map, it's red, maybe. And I really wanted to see if we could use these same sort of techniques to ground truth some of this this state data. And so the hypothesis was that algae near areas of high cesspool and septic tank density or wastewater injection wells will have higher delta 50N and nitrogen percent values compared to the locations with, no wastewater sources or few wastewater sources or low density of wastewater sources. So this was kind of the map that got me started from Whittier and Al-Qadi, 2009. This is kind of their pilot study to do this for the Hawaiian Islands. They've since done all the major Hawaiian Islands. And you can see that Oahu looks like it's got a pretty serious problem in places. We've got Haleiwa in the North Shore, going up the North Shore here, all these parts of red, Kaneohe Bay, Waimanalo is one of the most dense areas, even where we even have great, sewage facilities and infrastructure. We still have a fair amount of red areas right here in the heart of Honolulu, Eva Beach, the west side, all kind of potentially problematic areas. But this is all just showing where the density of these are. It's not saying that that's getting into the groundwater so much. It's not saying it's getting into the ocean water. It's just here's where all the cesspools are. And my question really was, well, is it impacting the coastal water? Is there a connection? And so I kind of identified all these areas, and I wanted to test algae in these areas, but also the greener areas for comparison. So there's about a little under 15,000 OSDS sites on Oahu, 40,000 injection wells, 40 injection wells. So I collected ova at these sites, and you can see the corresponding values up to 19.1 for delta 15N. And you can kind of see the relationship. So all these little red marks, these are individual data points for cesspools and septic tanks. And you can see that there's areas around Oahu that do have red and orange values, and they are sometimes close to areas that have lots of high density of septic and cesspools. Acanthophyra was also collected, and we get fairly similar results with both species. So in order to look at the data, not do any fancy math, just look at the data and say, well, what would be a wastewater indicator? Again, we're going back to high delta 15N and high nitrogen percent. So a lot of nitrogen in the tissue is looking like it comes from a wastewater source. So if we combine high delta 15N, I chose above 9, and a percent N value of above 2%, and we kind of choose areas that satisfy both, where the algae have both of those items, we come up with Haleiwa, North Shore, Kahuku area, Waimanalo, Black Point, and Nanakuli. And so, surprisingly, these were, well, I guess not surprising, but these were all the same areas that were identified in Whittier and LKD's paper as being potentially problematic. And again, they didn't test the coastal water. They said because of the density of these things and the depth of groundwater in these coastal plains, it seems likely that this could be impacting the coast. But they weren't sure. They just did a modeling study. So this is kind of one of the first studies that really links, or at least points to the link between OSDS density and coastal water quality. So I worked with Whittier a bit, and we're kind of still in prep on this paper, but he modeled the groundwater nitrogen values from each of those sources, and then tracked that towards the coast to come up with information that looks similar to this. So in these areas where we have a lot high density, we have kind of this high density area here producing concentrated nitrogen in Haleiwa on the west side. There's an area here near the base, and then in Waimanalo, it's hard to see there with the seaweed information laid over it. And when you compare these two in a regression format, geographic regression, we find that they relate very well. Ulva tissue at least does. So ulva tissue delta 15N is related fairly well to estimated groundwater nitrogen. And for whatever reason, I don't know why, probably because of the lower sample size, but Acanthophora did not show a very good relationship. So again, going back to ulva, we use it a lot for this type of work. It seems to be a fairly good alga. So looking a little bit more in Waimanalo, this is Waimanalo wastewater treatment facility. It's an injection facility that does about 500,000 gallons a day, so a little bit different scale. Kahului 4.5 million, Waimanalo 500,000, but it's Oahu's largest injection well. Delta 15N of the effluent has a similar value to what we found in Kahului, 24 per mil there, and that's that's in the range of many secondary treatment facilities. Drinking water wells in the back show up around 7 per mil. Coastal water sampled out in front of the facility here, that's about 600 meters away at 23. So nearly identical delta 15 value of the coastal water sampled at the beach versus the wastewater injectee. And we can't ignore the fact that there is a high septic and cesspool density. Again, this is one of the highest, the most dense areas on Oahu for OSDS. And if you're familiar with Waimanalo, we call this the beach lots. There's kind of this old grandfathered in area here with a whole bunch of septic tanks and cesspools. And the water table, I mean, if you open these cesspools, you can see it fluctuate with the tides. There's obvious connection between the ocean tides and this area. And so over 2 years, I deployed algae here, and what we found was that our highest values for delta 15N were concentrated in this estimated kind of high plume area. And as we got away from the wastewater facility and this high dense OSDS, those values decreased to somewhat ambient values in the 0 to 4, 5, 6 range there. Again, we have to kind of reference the drinking water wells in that area, so that would be groundwater tucked way back at the mountains there. All right, so another great Maui question is, is this happening here? This is the Whittier and El Cadi. They did this again for all the islands, and they kind of took it a step forward, and they started predicting shoreline impacts a little bit in this paper. But you can see the red areas are where we have a very, very dense OSDS. All right, coming in on the close here. We're doing similar work on this island of Tutuila in American Samoa, comparing minimally impacted sites, Batia and Oa, with some more heavily impacted sites, Faga'alu and Paula Lagoon. And again, we're doing similar methods. We're collecting local seaweeds, and we're also deploying local seaweeds. This time Hypnea. There was no ova there. I would have loved to work with ova, but I just didn't find it. It's pretty, a bit of a bummer that we didn't find it, but kind of amazing at the same time. We did find ova, but not the same Lactuca broadleaf type that's really easy to work with. It was more of a hairy one that was stuck to rocks. Yeah, I don't have a picture of it. So this work is kind of, it's going in new directions. We're working on using DNA from biofilm. So this is kind of a biofilm setup. We have these horizontal sediment plates and vertical sediment slides. And so we basically deploy these in the ocean for a period of time. We pull them off, we scrape them, and send the DNA to the lab, and we get a picture of what the microbial community looks like. And we compare that among sites. We compare that to the seaweed information. We compare that to the water quality information, and we try to build parallels. We're also working with other researchers. We're also sampling again wells, streams, springs, coastal water, doing water budgets for these areas. We're also doing radon gas, as we did on Maui, to estimate groundwater flux and nutrient loading, using similar methods, the kind of coastal tow and the 12-hour deployment kind of stationary surveys. And we're working on developing with another researcher protein expression analyses, where we're looking at kind of gradients of nutrients. So we'll compare the protein expression. So these are proteins that are expressed in high nutrient environments from corals that are in high nutrient environments with those that are not, and trying to build parallels with these other data sets that we have in identical locations. So our alga deployments look something like this. I always pre-treat my algae in what I call the algae torture chamber to reduce the tissue nitrogen. So I take it off the reef. It might be full of nitrogen. I half kill it / starve it of nitrogen till it, it can cut the nitrogen down to like a third. So when you put it out in the reef, it just sucks up everything like a sponge and really reflects what that area a lot better than if you had put it out there full of nitrogen. It wouldn't take up any. It would just sit out there and maybe slowly lose nitrogen, maybe slowly take it up. But if you can really squeeze that sponge of nitrogen and let it fill back up again, that's really ideal. And we deployed them in cages. So in summary, SGD is a transport pathway for anthropogenic nitrogen in coastal areas. Again, it's a very ubiquitous process. It's probably happening most places you go to the beach. You just might not know it, or just might not be happening very much. There are other areas where there's cap rock and it physically does not happen, but I would venture to guess that even cap rock has many cracks and lava tubes and things like this. Nitrogen loading the coastal groundwater can result in elevated nitrogen in marine water and in the plants that grow there. It can, through this kind of invasive algae growth, can lower species diversity. And the Delta 15N values indicate that wastewater is a source of nitrogen, and it's present in Kahului Bay, many sites on Oahu, and also we're finding evidence of American Samoa at our impacted sites. Large-scale application of fertilizer was, and I changed, it used to say is, and I changed it was because fertilizer is not being applied anymore, but I think it's still happening. That aquifer is still full of fertilizer. It's probably going to come out I don't know, I don't want to put a amount of time on it, but probably it's likely for a decade. It could be 3 years. I'd be happy if it was less, but we don't know, and I think that's one major reason to really look into this a little more. So, source to Kuau Bay and also Ma'alaya. And so this has a lot of policy considerations. I think really understanding that groundwater, how much it influences our coastal water, we should look at ways to decrease nitrogen in coastal groundwater and think about the impact and the potential for that has on reef recovery. Methods to do this would include maybe introducing better nitrogen reducing treatments at wastewater treatment plants, reusing more of the water and putting it elsewhere. Upgrading existing cesspools is a big one. We finally, I've been working with Surfrider for many years, and we finally were able to help ban cesspool development here in Hawaii, which is about 60 years after the last state to do it. We're the last one, so that's kind of a huge win for Hawaii. And so now we have the task of, now that we're not doing any new ones, we should really be upgrading our old ones. So if you're not aware, there is a tax credit out there that we just got passed through the legislature recently that allows for people in certain places to upgrade their cesspools. And I think this is being done with the science in mind. We're looking at setbacks from shorelines, from streams, the depth of groundwater, the density of cesspools in the area. And I think we can't ignore the fact that sea level rise is very likely, and that's going to decrease that depth to groundwater and possibly inundate some of these septic systems in low-lying areas. If you look at some of the SOAS predictions, we have coastal flooding from groundwater inundation in many areas, and so I think that this is definitely going to impact how nitrogen and pollutants are transported from these low-lying areas into the ocean.
Just one comment on
Yes.
that slide, Daniel. You had said, it wasn't on the slide actually, but you said reducing the amount of water we inject and reusing the water. I just want everyone to know the jury's kind of out on how much of that nitrogen would get to the ocean. So even if we reuse all the water, there still might be a need to remove nitrogen at the treatment plant before you reuse it.
Yeah, and that
And
was
we
kinda-
don't know the answer because no one's done that work.
Right, and that was kind of in the back of my mind as I said that. I think that that's definitely true. If nothing else, it may be better if it's not such a point source. But then you could also argue at least the point source is contained in one area, so
And you can
the jury's out.
treat
I
it,
think
right.
it really is.
Right. We don't know. We don't have the work to do that.
Yeah.
I mean, presumably it'd be lowered in concentration somehow through processes, but
Right.
we don't know how much, and is that enough to not harm?
Right. I agree. So, in conclusion, wastewater is likely impacting Hawaii reefs. These OSDS systems and injection wells are a source of wastewater to marine ecosystems. Algal blooms and reef degradation are caused in part by excess nutrients, but again, we can't ignore the role that herbivores play in all this. That contaminated SGD may be a chronic threat to coral reef ecosystems and potentially human health. And that this is really an economic, it's an ecologic and a public health issue. And we can do something about it. So,
You have the 4-point plan of what we should do about it?
oh, you're up next. So I just want to give some thanks to my funding agencies, UHM for hosting me all these years, and co-authors, lab assistants, field assistants, and all you guys here at the Resource Council. And yeah, I'd love to take any questions you have, and I don't have to fly home for a little bit tonight, so I'm happy to talk story and hang out. So thank you so much for listening. I hope I didn't bore you.
Questions?
I have a question. So your studies were done, I wrote these notes when we were looking at the slides of Kahekili. And that, the study said it was done in 2013, so has it changed since then? The effluent percentage, you had 64% effluent, so I was wondering if you could define, I know what effluent basically is, but is there a mixture, is there a definition that you're using for that amount? And have you studied it, has it changed at all since 2013? So I thought they had done tighter restrictions or something on the wastewater treatment plant there. So has it changed at all?
So the first question was, what is effluent? So we're using effluent in the manner of the water that's been treated, that's put in the injection well, and then flows away from the plant. So that's effluent. Has it changed since 2013? I think that, I alluded to this earlier, that the water has changed. At a certain time during the study, there was no chlorination or UV being done, and so the water was going in with kind of a full bacterial load. And like I sort of alluded to also, that was kind of a benefit on some level, because there was this natural denitrification process that was removing nitrogen en route to the ocean. So when the water got there, it had a lot lower nitrogen than when it went in, and it was a lot warmer, interestingly.
Because it was warmer, did it create other bacterial problems, or?
I'm not, I can't say.
Okay.
That study was not really studying the bacteria of the situation. It was more the nitrogen and the dye to estimate the amount of effluent and flow that was happening. So I can't really comment on the bacterial issue.
Okay.
But I do think it's interesting that when the state addressed the potential bacteria problem with the chlorination, that the nitrogen values went up. And I'm interested to see if the temperature went down.
Yeah. Okay. And so you said that was 64% effluent that was going through. So
On average.
On average. So was it dissipating in its route, or just?
That's when it came out of the springs that they were measuring. So at
Okay.
times you could actually see the dye with your eye coming out. But that's, 64% from, so if it goes in at 100%, the water that's sampled is mixed 64% with that effluent that went in, and the rest would be ocean water or other water sources.
Thank you.
You kind of brought it up with your question about bacteria. I think it's important for us to remember, because you're concluding, that this wastewater is reaching the ocean in all these areas, and that, it's significant, like public health and ecologically, but we're only talking about nitrogen tonight. So can you just say something about potentially what are the unknowns or things that we know are in wastewater that might also be getting to the ocean, and are there any studies or concerns about that?
Right, so I think with injection and even cesspools and septic tanks, there is a fair amount of filtration that happens, particulate filtration. One of the most effective filters that people still use is a sand filter, right? So if you think about those sediments that groundwater is discharging through, in some places, I would venture to say in most places, it's a diffuse discharge. So there's a pretty good filtration in that sense. You're having a lot of particulates come out. You're having, and this is, I'm just totally hypothesizing here. I haven't measured this. But I'm guessing that the water coming out there does not have the same bacterial load as it goes in, because it's being physically filtered through sand, through rock. Now, there are places that I've worked at where that's not the case. There's a lava tube. And you can see this in the back of Honokohau on the Big Island. There's a big hole in the reef in the back of the harbor where super cold water is spilling out. It's very high in phosphorus. It's very high in nitrogen. And we took a little field trip uphill one day, and we found the sinkhole that the wastewater facility, they pipe their wastewater after it's treated uphill, and then it goes into a sinkhole. And that's presumably flows directly to the back of the harbor. And so in that case, there's probably less filtration, because you have this kind of natural lava tube conduit, high permeable area. And in that case, I would imagine there would be less filtration. Is that a...
Lahaina has
Kind
that.
of answers part of it, but there's,
just a lava tube.
we need to understand that there are endocrine disruptors, there are, you know, anything that any of us flush down the toilet that isn't removed at the treatment plant is also going out. So, you know, I think that the nitrogen's the obvious thing, and
It's
the
an
one that can
indicator.
be best delineated at this point.
Caffeine is good also.
Yeah, but this is telling us, you know, the nitrogen might just be the tip of the iceberg as far as how it's affecting fisheries and coral and things like that. But it's kind of a gross thing because literally, you know, the nitrogen is causing the overgrowth of the reef with algae and the killing of the reef. So it's not the refined kind of toxicity or something. You can't even see that yet because we're
Right.
still dealing with the gross stuff. But
Sure.
so I just want everyone to understand, like, this is just the tip of the iceberg. This is a big problem that all of our wastewater is going out with perhaps not enough mitigation or treatment. And obviously, the more we reuse, like you said, there's all these pathways of the natural filters of soils and so forth. That, you know, even if we're reusing for irrigation water, hopefully that is better, but we don't know how much is enough. So I think there's a lot of work to be done, is what I'm trying to say, and I think
I
our
agree.
state really needs to invest in it, because there are a lot of reasons to handle our wastewater better, as well as our land use practices and, you know, how being more judicious in what we put on the soil and how we handle it.
Related question, can we use algae? Does algae integrate all these other substances, heavy metals, pharmaceuticals, yada, yada, yada? Can we use algae in the same way that we're using it for nitrogen?
To remove some of these other.
Not so much for filtration, but does it accumulate it so that we can use it as a measure?
Is it a sponge in that sense for other items on the reef? That I don't know a whole lot about, honestly. I haven't. I think that certain plants do accumulate metals and such more than others, and that's why they're used for remediation efforts. But the type of algae I was using and the other common algae on the reef, I haven't really looked into that a whole lot, but I'm definitely interested.
Are you able to differentiate ag fertilizer and golf course, hotel fertilizer?
Not exactly. That would be amazing if you could say which brand of fertilizer per se that you were detecting. You could. Yeah, no, you really can't. Sorry, the signals are just too similar, and the environment. I just don't think with this method it's possible. I'm sure, someone could design a method that could get the signature of that fertilizer chemically and somehow detect it elsewhere, but not with the methods that we've been talking about.
Do you have other ideas about how to use these techniques to solve pollution problems?
Well, what type of pollution problems?
Well, like I'm thinking, I think Megan Daler did at least one paper on this, that if you wanted to, if you're a pollution control person like I am, and you want to know what is the number I put at the end of pipe in that NPDES permit or in that injection well permit, I need to know the dilution of what's happening, so out in the mixing zone that you've plotted out, but I need the volume or the dilution factor. So can you get that?
So your question is, can you get a dilution factor?
Like in that whole mixing zone,
Yeah.
what is the percent effluent versus the percent other water?
I think, so with the algae, it's tough because, and just Delta 15N in general, I want to kind of make this point really clear. The Delta 15N, a higher value doesn't necessarily mean more wastewater or a higher wastewater signal or higher denitrified signal. It's just indicative of that signature of the source. Okay, it signifies more denitrification, but that doesn't mean that there's more nitrogen. It could actually mean that there's less nitrogen, because denitrification means taking away nitrogen, the denitrifying. So, I think that when in terms of determining how much nitrogen is actually in the water and the dilution factor, that the percent N is going to be your best bet. Percent N is really tightly linked to what the water quality is. But if you're trying to think of like the type of calculation you're talking about,
No, we're talking about the actual volume of the
Yeah.
water. That's what we're trying to get.
Yeah.
The volume.
I think the best way to do that is probably not with the seaweed and stick with the geohydrology, which is calculating the groundwater discharge, the percent of effluent in that discharge, and then working from that angle with the volume of the, with the bathymetry of the area and the mixing that is present. I don't know, yeah, I would have a hard time, I could continue to work on that, but using the algae, do you have a suggestion?
Well, I think what Megan did, like your cages were at the top.
Right.
So you get a two-dimensional picture, a
Right.
two-dimensional map, but if you went down more
Right.
and mapped that same thing, then you would get a 3D
I see,
model
okay.
and a volume.
I see what
Yeah.
you're saying, yeah, so more three-dimensional
And then you
picture,
could get
yeah.
a dilution factor to your volumetric.
Gotcha. Yeah, Megan did do that out in Calcula. She did a three-dimensional deployment where she had like top, bottom, and middle, more or less. And the results were really interesting because what the kind of take home from that paper was that it was so variable from month, because she did month after month, and she would take the seaweed in every month, and every month, like the seeps that were hot one month would be, when I say hot, I mean they were flowing high with wastewater nitrogen or high delta 15N signal, were might not have been the next month very similar, and that would have moved somewhere else. So it was very dynamic, and I think that's kind of the takeaway. So I think, yeah, you could probably do something like that and average it over time and pull that out. But yeah, I think that was really interesting at how variable the environment was in that sense. It wasn't very static, and that might be due to mixing, it might be due to conditions, or just other factors that we haven't considered. Steve had a question.
I just had a comment regarding Robin's concern about the endocrine disruptors and pharmaceuticals. What some municipalities are doing, such as in Orange County, where they actually recharge their drinking water aquifers with treated wastewater. They use a process called advanced oxidation, where they couple ultraviolet disinfection with some type of oxidizing agent, such as hydrogen peroxide or ozone. And that does a pretty nice job of removing.
It'll destroy it.
Yeah, it takes the endocrine disruptors and pharmaceuticals out. And then Larry mentioned algae. There's actually been some companies that have approached the county about using algae to help scrub excess nutrients and compounds out of the wastewater.
As a treatment.
Yeah, as a treatment.
Yeah.
And then there's actually a gentleman who is proposing some type of a distillation system in West Maui to take the effluent from the Lahaina wastewater facility and put it through existing pipelines that are in the ground, pump the water up, and then kind of distill that water and make almost pure, almost drinking water out of it. And so there's a lot of great ideas out there.
Yeah.
It's just a matter of having the courage to move forward in some of these ideas. Energy, yeah. He would actually use a hydroelectric system to help recover power from the water coming back down again. So there's a lot of really great minds out there. It's just a matter of
Part of
having the will to do it.
my third PhD, the third segment of my PhD proposal was going to be actually growing some of these seaweeds in wastewater treatments and then fermenting it to methane gas. And so that was, an area that I was interested in, using wastewater to energy through algae and creating fertilizers and things along the way. But I just can't do it all. You propose the sun and the moon, and you gotta graduate someday. So yeah, I never got there, but I'm definitely fully interested in that route.
You can use wastewater to irrigate non-food agriculture,
If
like
it's
hemp.
If it's to a certain standard,
R1.
yeah.
Well, actually, if it's R1 water, you can use it to irrigate edible food crops, where the water directly contacts the edible portion. If it's R1, which is the highest level.
Full
of
reverse osmosis?
No, R1, not RO. R1, which is what the county actually produces at Lahaina and Kihei. And R2 is good for like.
It still contains the endocrine disruptors.
Well, but the Department of Health does not regulate that, but.
Right, the R1 talks about turbidity and
Turbidity and
bacteria.
bacteria, that's it. And R2 would be more for like, fruit trees where you irrigate the ground, but not the edible portion. So, it's being done. A lot of our food crops that we imported to Hawaii are irrigated with R1 water. Monterey, the salad bowl of the nation, uses R1 water to irrigate broccoli, artichokes, all types of food crops that people eat all the time. So it's safe,
Any other questions?
Yeah, just to clarify, you said something about arginine expression was that as a nitrogen or as an effluent in areas that you have high nitrogen or areas that you have effluent?
So in the way that the study did it, they developed a metric they called the nitrogen footprint. And so that was basically parsing out land use into areas that have more nitrogen input to those areas. And they monitored the occurrences of turtle tumors and related that to the nitrogen footprint of the areas. And that was the first study that was done. But basically the idea is that when algae have excess amount of nitrogen, they store it. And that's why, the algae pictures that I use that are brilliantly green, that's because they're just loaded with chlorophyll. And they use actually chlorophyll as a storage molecule. They also use amino acids because they're high nitrogen, like arginine. So they'll produce excess arginine, presumably as a storage molecule. It may have other, it's also a kind of a building block amino acid in general. But so these excess arginine in the diets of sea turtles are presumably exacerbating the turtle tumor situation.
Was that ever used as a protein analysis to figure out where these effluent exist, as a tracer? Just to do a protein analysis and say, we have above higher, we have a certain percentage of arginine as an amino acid, or, not necessarily protein analysis, but the short chains of amino acids. Do you know if that was done?
I know that the amino acid profile of a lot of these seaweeds was was done and related to the occurrence of turtle tumors. But in terms of, you're talking about the proteins in the wastewater itself, or just in areas?
Using the protein analysis to figure out where the algae is as a marker.
Yeah, that was done. And it lined up pretty well with the occurrence of turtle tumors. So it seems that they're related, and there's a lot of evidence that points in that direction. But that wasn't my study, that was just my colleagues. But related, And here on Maui, I've been to Ho'okipa. In your, you guys have your boots on the ground here, do you see turtle tumors occurring still? And do you think that it has been reduced at all in the last 5 years? Yeah. I think it has to. That's kind of my notion too. Yeah, and so the reason for that, anyone's guess, I don't know. Anyways.
I was thinking the same thing I was going to say.
We'll figure it out. What seaweed not to eat? I don't know.
Any other questions?
Daniel will be around.
All right, well, let us thank you again, and we'll move on.
Squeeze like